Let's roll. So last time we discussed about the Biot Savart's law, where a filament carrying certain amount of current is going to generate magnetic field around it, and we can calculate that magnetic field, let us say at point P, which is at a distance r, and we have angle theta in between the line having the current and the vector joining the current filament and the point. Okay, so we do have some observation. Do remember that this is empirical, that is observation formula. The amount of magnetic field intensity generated is directly proportional to amount of current, is directly proportional to the length, is directly proportional to the sine of the angle in between the two, and inversely proportional to the square of the distance in between them. So this behavior, the sine angle, okay, the sine angle behavior can be explicitly written in terms of the differential length and the unit vector associated with the direction. Okay, so we can put dh bar is equal to bar cross ar, and by a definition of the unit vector we do have ar cap is equal to r bar upon magnitude of r bar. So we have rewritten the expression as dh bar is equal to I dl bar cross r bar upon 4 pi r cube. Okay. Then we have noted down all these expressions in our notebook. Then we went for applying the Biot-Savart's law to get magnetic field intensity due to straight conductor, and second is circular loop. Then we are going to study Ampere's law, where we are going to apply it for an infinite sheet of current, and we will try to get the expression of electric flux density, sorry, magnetic flux density. Okay, we have seen the first derivation about magnetic field intensity due to infinite conductor. We have this expression h bar is equal to I upon 2 pi r a phi cap. Okay, so here we have assumed that our current carrying filament is placed on the z axis, and we will have a kind of magnetic field around the z axis. And do remember that we will have this direction like this way, a phi cap. Okay, a phi cap, the direction of the magnetic field around the current carrying filament. Okay, this is very important. So we do have some observations. Okay, this Fi cap came into picture since we have assumed that our current carrying filament is on the z axis, but in general we can write down if infinitely long conductor is placed anywhere, we want to generalize our expression anywhere in the space, then direction of magnetic field strength at field point is represented as an cap. Okay, where an cap is nothing but the cross product in between the unit vector associated with the length of the current carrying filament and the unit vector associated with the vector joining the source and the observation point. Okay, यहाँ पे लिखा है AL is the direction of the current in the conductor and AR cap is the direction of a vector from source to the field. So H bar is equal to I upon 2 pi R A N cap. Okay, तो in general आप ये formula use कर सकते हो. Then we will go to next case where magnetic flux intensity, magnetic field intensity due to infinite conductor, we want to get an expression. For this purpose, please observe the geometry very carefully. Okay, assumptions made. We do have current carrying filament on the z axis. Okay, and its z limits are from a to b. Okay, so z is equal to a to z is equal to b. We do have a vector r bar which is joining a very small length dl bar, okay, of the finite conductor and our observation point P. Okay, whenever we want to get an expression of r bar, we always do require the coordinates of the source as well as the destination. Here the point P is considered onto the z axis, sorry, considered on the xy plane. Okay, so therefore its z coordinate is 0. We are dealing with the cylindrical coordinate system, the coordinates for point P will be r phi 0. This z is equal to 0 because we have assumed that point P is on xy plane. Okay, point P is on xy plane, therefore z coordinate is 0. For the dl bar element, we will have 0 phi z because this dl bar indicated by the yellow portion is on the z axis at some height above the xy plane. Okay, so we will have the coordinates for dl bar as 0 phi z, and now we can get an expression for r bar. We can get an expression of magnitude of r bar, and we will have our regular expression dh bar is equal to I dl bar cross r bar upon 4 pi r cube. Okay, we do have some different notations over here in terms of the angles as well. Okay, if you observe alpha 1, it is the angle in between the line perpendicular to the z axis. कौन सी line perpendicular to the z axis है? ये वाली. Okay, this is the line perpendicular to the z axis because this line is on the xy plane. The dotted line is on the xy plane, and we know that xy plane is perpendicular to the z axis. So alpha 1 is angle in between a line perpendicular to z axis and a line joining the lower end of the conductor. Similarly, we do have alpha 2, which is an angle in between a line perpendicular to z axis and a line joining the top end of the conductor. Okay, of the current carrying conductor. So how we are going to proceed? First of all, we are going to apply the Biot-Savart's law straightforward. So we will have our assumptions. Consider finite length conductor placed on z-axis. Consider point P as shown in figure. Here is angle made by the bottom of conductor with the horizontal axis, whereas alpha 2 is angle made up by top of the conductor with the horizontal axis. By Biot-Savart's law, we do have dh bar is equal to I dl bar cross r bar 4 pi r cube, where r bar is expressed in way. The two values of d are az cross ar cap upon 4 pi r square plus z square raised to 3 by 2. I have skipped one step over here, very important step. Okay, very important means what? I want to put a cross product in between the dl bar and the r bar. Okay, so az bar ar, az cross ar cap, it is written over here, and az cross az, this will be 0. Okay, the cross product in between the same vectors is always 0. Now we want to put something over here for this bracket. Okay, az cross ar cap. If you do remember about the cross product, ar cap cross fi cap gives us az cap, fi cap cross az cap will give us ar cap, and az cap cross ar cap will give us fi cap. So we do have this understanding. Okay, if you remember ar, fi, az, ar cross fi will give us az, fi az, fi cross az will give us ar cap, and az cross ar will give us fi cap. Okay, so we have rewritten our expression as h bar is equal to, now we want to have the complete electromagnetic flux density equal to integration a to b, that is the length of the conductor, I dz r a phi cap, we have replaced the bracket, 4 pi r square plus z square raised to 3 by 2. Okay, now we want to make some assumptions over here to solve this integral. Let us assume that z is equal to r tan theta, therefore this gives us dz is equal to r sec square theta d theta. Okay, now let us try to get the limits. If z is equal to a, then theta is equal to alpha 1. Okay, this is our assumption because the angle in between the lower and the horizontal axis is alpha 1. A is the lower end. Okay, therefore we have considered the alpha 1 angle which is with the lower end, which is with the bottom of the conductor. If z is equal to b, then theta is nothing but alpha 2. Put these values and this one into the above expression of h bar. We will have h bar is equal to take out the constants outside the integral. I is equal to 4 pi integration alpha 1 to alpha 2, and we have replaced all the terms with our assumption. So r square and only r is remaining in the denominator. Sec square theta d theta 1 plus tan square theta raised to 3 by 2 a phi cap. Solving this one, we will end up into cos theta d theta a phi cap, and the limits are alpha 1 to alpha 2. So we do have uh, integration of cos a sine and putting the limits. So sine of alpha 2 minus sine of alpha 1 a phi cap. So this is very important expression, okay, where h bar is equal to I upon 4 pi r in bracket sine alpha 2 minus sine alpha 1, or I can say that sine of the top end angle minus sine of the bottom end angle a phi cap. Okay, this a phi cap came into picture because we assumed our conductor to be on z axis. Otherwise, while solving the numerical, we may need to calculate the a phi cap, that is a n cap expression. Okay, here in this formula we do have some conventions. Okay, now you can observe in the given diagram, for alpha 1 we are going upside, for alpha 2 we are going upside. So whenever we are going upside, all those angles are positive. And if we do have a kind of geometry like this, we do have our conductor at this position and we do have point P. So we do have a dotted line, and we have joining a line joining the top end as well as the bottom end. So here over here alpha 1 will be negative and alpha 2 will be also negative. So if we are going in a downside, we will have a uh, negative angles. So we do have some conventions over here. If point P is above the top above the top of the conductor, so both the angles are negative. If P is below the end of the conductor, both the angles are positive. And if point P is in between the two ends, so if we have our conductor and P is in between the ends, we'll have line over here. So this one is alpha 2 and this one is alpha 1. So alpha 1 is negative and alpha 2 is positive. These conventions are very important. Okay. uh, have you noted down the derivation? Someone, yes or no? It's okay. Just I want to make confirmation. If noted down, okay. If not noted down, it's also okay. But please let me know what you have done. Noted down or not?
Yes,
Uh,
sir.
okay, great. Okay,
Yes, sir.
okay, fine. Next, we do have magnetic flux intensity h bar along the axis of a circular loop. Once again, we have some assumptions over here. Consider a circular loop carrying certain amount of current I, which is placed on the xy plane having radius r. Okay, radius r. Let us consider a very small element of the circular loop, which is called as dl bar. Consider a point P on the z axis, which is our observation point. Okay, its coordinates are 0 0 z. Okay, and we have a vector r bar joining the dl bar and the observation point P. Okay, so whenever we do have a vector r bar which is going this way, I guess you do remember we can split any vector r bar, okay, in its two components, normal component and component, or two components perpendicular to each other. So if we have a vector r bar, it can be split into component along the z-axis and a component along the radial direction. Okay, along the radial direction. So we do have this setup, our experimental setup, our mathematical setup. Okay, and using this setup, we are going to have our mathematics. I repeat, we have a circular loop having current I placed on the xy plane with radius r. Let us consider a very small amount of filament dl bar. Consider point of observation P on the z axis. The coordinates of P are 0, 0, z. Vector r is joining the source and the destination. Okay, and let us see what we have as an expression of h bar along the axis of the circular loop. Okay, so axis है z axis. Okay, it is passing through the center of the loop. So we do have r bar. Okay, we do have r bar as z az cap minus r ar cap. Okay, sorry, extremely sorry. Mm, I will make few modifications over here. I want to make p as 0 phi z and the coordinates of dl bar are r phi z. Okay, so we do have this one r bar as z a z cap minus r a r cap, where and also the magnitude of r bar is, let me put down in this way, magnitude of r bar is equal to r square plus z square. Dl bar is r d phi a phi cap. Very interesting change over here. Since dl bar is a part of the circular loop, we do have r d phi a phi cap. Let us put it into the Biot server's law, where dh bar is equal to idl bar cross a r bar upon 4 pi r cube. So dh bar is equal to I r d phi a phi cap cross z a z cap minus r a r cap 4 pi r square plus z square raised to 3 by 2. Okay, so we will have the cross product in between the a phi a z in between the a phi a r. Okay, so accordingly we will have I wrote the expression once again. Okay, so a phi cross a z cap will give us a phi cross a z cap will give us a r cap, whereas a phi cross a r cap a phi cross a r cap will give us minus a z cap. So minus sign will be dissolved with this minus sign, so we will have plus r a z cap. So putting these values into the expression, we will have dh bar is equal to I r d phi z a r cap plus r a z cap upon 4 pi r square plus z square raised to 3 by 2. Okay, so all the terms over here are as it is, just we made a cross product with a phi component. Okay, nothing else, we have changed nothing. Then we do have dh bar is equal to I r t phi r a z cap 4 pi. यहाँ से है ना एक एक interesting change happened. All the AR cap terms got vanished. Why? जैसे यहाँ पे DL बार है, ओके, वैसे ही on the opposite side में भी DL बार होगा. Okay, so this will also have, sorry, this will also have its vector going towards point P. Okay, so we will have the vector due to this DL bar which is present at the opposite side. सो इसके लिए भी एक DH-Z component आएगा और इसके लिए भी एक radial component आएगा. Now this radial component is opposite direction with this radial component. Why? Because we do have a symmetry over here. जैसे DL bar यहाँ पे है वैसे ही DL bar opposite end में है, और due to these symmetrical components we do have opposite radial magnetic field intensity vectors. And since these two vectors are opposite in direction, they will cancel out, and therefore we are left with only the z component. Okay, so due to symmetry along the axis, only a z component exists and ar component will cancel each other. Okay, cancel each other. So we do have this term, and we can rewrite this one as dh bar is equal to I r square d phi upon 4 pi r square plus z square raised to 3 by 2 into az cap. Now we want to get the complete term. H bar is equal to, take out the constants. Okay, we do have only d phi, so everything is constant, and we know that the limits of d phi is 0 to 2 pi always. So we can put it into the formula, and we will have I r square upon 2 into r square plus z square raised to 3 by 2 into a z cap. Okay, क्यों? क्योंकि इस इंटीग्रल की वैल्यू थी 2 pi. So pi gets cancel out, and 2 ones are 2 and 2 twos are 4, and we are left with this expression. Even though this expression looks very weird, जहाँ पे r है, z है, everything, this is how actually this derivation gives us an procedure and general procedure to apply Biot-Savart's law to any geometry. ओके, एनी ज्योमेट्री, कि भाई एनी ज्योमेट्री है मतलब आपको आर बार फाइंड आउट करो, डीएल बार फाइंड आउट करो, इफ नेसेसरी डू द क्रॉस प्रोडक्ट्स, एंड इफ एट ऑल पॉसिबल apply the symmetry and cancel out few terms and get your final expression after solving the integration. So kind of expression. So probably you might have noted down this one, and if not noted down, probably you have taken a screenshot. Okay, and this is a h bar magnetic field intensity along the axis of the circular loop, and here with our assumption axis of the circular loop is z axis, which is passing through the center of the circular loop. Okay, if z axis is not at the center of the circular loop, we cannot apply this symmetry. This is very important that our z axis is passing through the center of the loop, and we can apply the symmetry so that the radial components will get cancelled out. Okay, due to opposite dl bars. Okay, due to opposite current carrying filaments. Okay, now moving on to next, we do have Ampere circuitous law. You have studied this one. Let us read the statement. The line integral of magnetic field intensity. The line integral, okay, of magnetic field intensity gives the current enclosed in that loop. Okay, current enclosed in that loop. First, apply the right hand rule and then decide the direction that you should integrate around the loop. Okay. Now, you may recall from your school time also, and maybe from the physics, if we do have certain current carrying filament, it is going to have the magnetic field intensity around it. Okay. So we do have two approaches. Current produces magnetic field, which is given by the Biot-Savart law. Okay. Which is given by the Biot-Savart law. And now if I say that, okay, I know the magnetic field intensity and I want to find the current in opposite direction. Okay, opposite direction नहीं, लेकिन h bar पता है and we want to get a amount of I. Okay, so we can consider an loop around a conductor. Okay, geometrical loop लेते हैं, मतलब kind of circular loop or square loop or arbitrary loop also. If you integrate magnetic field intensity on this loop, okay, on this loop you have considered, can get an expression for amount of current passing through the conductor. Okay, यहाँ पे you can use the right hand rule as well. आपको जो पता है, it says if the right hand thumb indicates the direction of the current, then the curl of the fingers around the conductor indicates the direction of the magnetic field. Okay, magnetic field. So knowing this Ampere circuitous law, we want to apply it to an um, let us go for a derivation before applying it. Let us go for a derivation. We want to have Ampere's law from the Biot-Savart's law. Okay, Biot-Savart's law pata hai, and we want to have the mathematical jigglery over here. Let us see. According to Biot-Savart's law, we have H is equal to I upon 2 pi R. Okay, we are considering an infinite conductor. Okay, H is equal to I upon 2 pi R. We know that B is equal to mu H, so therefore we can write down B is equal to mu into I upon 2 pi R. Okay, mu is nothing but the permeability of the medium. Integrating B bar around a closed path, we get, okay, a big expression. Let us go step by step. So we have integrating B bar around a loop, and this loop is a closed loop. Very important. Your loop has to be a closed loop. So we can say that, okay, B bar dot DL bar integrated over the closed loop. So we can write down it in terms of the magnitudes as B into DL integrated once again over the same closed loop, and take out the B as a constant because it is going to be a value, and in closed loop integration of DL, which will give us the complete. If you are considering a circle, it will give us the circumference. Okay, so B into L, that is the complete length of the circular loop, and we know that circular loop का circumference होता है 2 pi R. Okay, and also we know that B is nothing but mu I upon 2 pi R, which is from the Biot-Savart's law, and this is from the below step is from the general integration. So put the term for B as mu I upon 2 pi R into 2 pi R. So 2 pi R gets cancelled out, and we have mu I. Okay. So we can rewrite it as, okay, ये जो यहाँ से उठाया, so integration और यहाँ से, okay. So I is equal to closed loop integration of B bar upon mu into DL bar. Okay, and B bar upon mu is nothing but H bar dot DL bar. Okay, so this is how we have started with the Biot-Savart's law. We applied the mathematics and we end up into the same expression. I is equal to closed loop integration of H bar dot DL bar. Closed loop होना बहुत ज़्यादा ज़रूरी है. Okay, if I say that select appropriate expression for Ampere's law, अगर ऐसे आता है and you have expressions like this, DL bar or I is equal to H bar dot DL bar, okay, or I is equal to H bar dot DS bar, or I is equal to closed surface integration of H bar dot DS bar. So definitely you are going to check this one, tick this one. Okay, so your MCQs will look like this, very confusing कि क्या है कैसे है. Even this circle in the integral do matter, closed loop. Okay, now we want to apply the understanding of the Ampere's law, and we are going to consider an infinite sheet containing certain amount of current. Here the K is considered as the current density. Okay, inside this infinite sheet. So if you observe over here, this current density is defined as Ky cap, because we have assumed that our current is flowing in y direction. The infinite sheet is placed in xy plane, on the xy plane. Okay, so Ampere's law always talks about a loop. Okay, Ampere's law always talks about a loop. Therefore, we have assumed one loop over here indicated by one moment, please. Please, one moment. Hello, I'm very sorry. Okay, so observe over here, we have considered one loop starting from 1, 2, 3, 4 and coming back to 1. So this is necessarily a closed loop. Okay, it has breadth B and height A. Okay, and we have decided the direction of the loop according to right hand rule. Okay, so point your thumb in the y direction and your direction of the curl of the fingers will give you the direction of the field around it. Okay, so we have assumed this direction as the right hand rule. We do have lots of assumptions and observations over here. Okay, let us go through them. What happened? One moment, please. It got hanged. My PC got hanged. Why it is happening? Okay, so we do have assumptions. Infinite current sheet placed in the z is equal to 0 plane, that is xy plane. Then second assumption, uniform current density k bar, which is indicated as ky ay cap ampere per meter. Now observations, very important. Here h bar dot dl bar over a closed loop will give us the amount of current enclosed by the surface, and which is nothing but ky b. Okay, ky is nothing but your direction of the current density, and b gives us the direction of the current density according to Ampere's law. Also, do remember that we do have h bar is equal to h0 ax cap for z greater than or equal to 0. Sorry, greater than 0 means what? Z greater than 0 means above xy plane. That you can consider the path 4 to 1, the loop path 4 to 1. Okay, वहां पे what is our assumption? h0 ax cap क्यों लिखा है? Because if you observe the direction from the path 4 to 1, it is in positive x direction. And for z is equal to z less than 0, that is below xy plane, we do have a direction from point 2 to 3, path 2 to 3, and here direction is in minus ax cap, so therefore we have minus h0 ax cap for z less than 0. Here h0, we are interested in the quantity h0, we want to get that value. Okay, so total magnetic field intensity can be given as, do observe over here, the closed loop integration of h bar dot dl bar, and now this time we want to split it up from different paths. Okay, path 1 to 2 plus path 2 to 3 plus path 3 to 4 plus path 4 to 1, that complete will give us the closed path h bar dot dl bar, and we want to put the values. Okay, for path 1 to 2. Okay, path 1 to 2, over here your magnetic field value will be 0 because your current is traveling in y direction, in horizontal direction, and path is your vertical direction. Path 1 to 2 has vertical direction, as well as path 3 to 4 has vertical direction. So in both cases you have h bar value is equal to 0, but that is not the case for paths 2 to 3 and 4 to 1. So for path 2 to 3 and 4 to 1, we have expressed the values, and we end up into an expression of closed loop integration of h bar dot dl bar is equal to 2h0b. Now combining all above equations, we can write down that h bar is equal to, okay, what we have done over here, we have placed this value, we have used this value. Okay, means what? over here, closed loop integration of h bar dot dl bar is equal to ky b. Also, closed loop integration of h bar dot dl bar is equal to 2h0b. And as said, we are interested in this value. So bb got cancelled out. So this will have 1 by 2 ky. So we have replaced this h0 value over here and over here, and we have this expression. Okay. In general, for an infinite sheet of current density k bar, okay, अगर in general लिखना है, so we can write down h bar is equal to 1/2 k bar cross an cap. An cap is nothing but a perpendicular unit vector. Okay, perpendicular unit vector. तो in general आप ये लिख सकते हो. Till date, the examiners are not interested in getting an expression of magnetic flux density due to infinite sheet conductor, but yes, sometimes they can ask you with a formula. Okay, with a formula that says what is the amount of magnetic flux density generated due to infinite sheet containing k bar as current density. तो उसका expression क्या है? तो expression you can get as an MCQ, but as a theoretical part, till date h bar due to infinite sheet conductor wasn't really choice of the examiners. Okay. With that say, uh, we have finished the first half of, not really first half, the 1/3 part of unit number 3, and next one is boundary conditions. We are going to start it in next session. Extremely sorry. We are going to start the boundary conditions in next session, and probably in next two lectures we will finish unit number 3 and we will start unit number 4. So everyone, please be attentive. Okay, please be attentive, otherwise you may miss very important discussions, and those important discussions are pretty much easy. Okay, so with that say, we will end today's session. Everyone, take care. Bye bye.